Record.
Hi everybody, welcome to week 5. Oh my gosh, we are going to look at the Chatelier's principle. I don't know how to say his name. I'm very bogan. But what we're going to look at is we're going to look at the effect of changing conditions on equilibrium and how we can manipulate that to produce more product in our industrial process. So, who remembers from Unit 3 the Chatelier's principle? Or the Chatelier's principle, or the Chatelier, I don't know, whatever his name is. Oh, so his principle tells us the effect of altering reaction conditions. And what effect will that have on the equilibrium position? Or how much product versus how much reactants we have when the reaction hits equilibrium. Equilibrium reaction is occurring both in the forwards and reverse direction at the same rate, or the reaction might as well not be happening. There's 2 reactions that we look at. I don't think we've gone through this. It could be wrong. I hope we haven't gone through it. So we could, if we look at temperature, pressure, or volume. We'll look at concentration. Of reactants and products. I will look at catalysts. So what we're going to look at is how can we manipulate temperature, pressure or volume, concentration of reactants and products in order to make sure our reaction is pushed towards the product side in our final reaction mixture. And we're going to look at 2 different reactions. We're going to look at the Haber process, Haber process, whatever I call it. My pens are dying. This is how we make ammonia. I've got a bunch of slides for this, but I like to do it on the board. I think it's a better visual. So there's someone out there that can create amazing resources that move, but I'm old school. Most are just old. So ammonia is N2 plus 3H2, and this tells us the reaction is happening in the forwards direction and the reverse direction at the same rate. And this produces 2 molecules of ammonia. I'll write this a little bit clearer. So I want you to write that equation down, and I want you to never forget it. Well, until you finish grade 12. Okay, so we're also going to write in here. Any ideas what that means? No, it says, yep, exothermic. It says that every time the reaction goes forwards, we release heat into the surrounding environment. Every time it goes backwards, it's absorbing. That's important to remember. I'll explain why shortly. Let's start with the simple stuff. So let's get rid of all that. Let's start with the simple stuff. This is an exothermic reaction. I'll just write that there. Now, anytime we make a change, this system is in a box. It likes to be balanced. Anyone studying biology, you think negative and positive feedback loops. It's always trying to come back to being chill. What's going to happen if I add reactants? Which way is the reaction going to go to balance out the fact there's now more reactants on this side? Think very, very logically. And I'm going to get some more pens. These are all done. Any ideas? If I add more nitrogen or hydrogen, is the reaction going to go forwards to counteract or backwards to counteract? Any ideas? Noah says forward. Noah would be correct. What if I added more product? Poppy says backwards. Poppy would be correct. Okay, that's the easy one. Let's look at, and we'll work up to temperature. What about pressure? If we think back to grade 11 when we did gases, what is pressure directly proportional to? Pressure is directly proportional to N, or the number of moles of gas. Remember that. So if I increase the pressure, And the system is going to want to counteract the increase in pressure. How do you think, which way would it go to counteract that increase in pressure if pressure is directly related to the number of moles of gas? Poppy says forwards. Why, Poppy? You are correct, but why? So it's going to push the reaction in the forwards direction because there's less moles of gas on this side. There's 4 over here and there's 2 over here. What kind of sound? So if we increase the pressure, the system reacts by pushing the reaction to the side with the least number of gas molecules, because it's trying to drop the pressure back down. What about if I were to drop the pressure? Which side is it going to favor? Because it's trying to bring the pressure back up. Noah says reverse reaction. Correct. It's going to go backwards because by increasing the number of moles of gas, we will increase the pressure. Problem solving question that was on last year's exam. What would happen if I halved the volume? Let me give everyone 2 minutes to have a think about what will happen if I halve the volume of the reaction vessel. Let me see if I can find some more whiteboard markers. All right, I'm down to my last 3 marble markers. Any ideas? All right. So the pressure is double if I halve the volume. So it's the same effect as increasing the pressure by 2 times. So the reaction will go forwards. All right. So the Haber process is exothermic. And this whiteboard marker is stuffed. So we have a change in heat. I think it's -92. So we know it's exothermic. Run over what that is. Every time the reaction goes wee forwards, it's releasing heat into the environment. Every time it goes wee backwards, it's absorbing heat. So what, again, we give 60 seconds to figure this one out. What would happen if I increase the heat? Or sorry, I shouldn't say increase the heat. Increase the temperature. Which way is the equilibrium going to send the reaction? So Kai and Poppy, why will it go backwards? What will going backwards do? So Poppy, they're all gases, but by going in the reverse direction, it's going to absorb heat and bring the temperature back down. What about if I drop the temperature? Which way will the equilibrium reaction go? It's going to go forward because every time we create the products, we're releasing heat to bring that temperature back to equilibrium. So, by that logic, what conditions should we have if we want to produce lots of ammonia? What should we do with the pressure? What should we do with the temperature? Which one should be high? Which one should be low? So Kai says to increase the pressure. So can I make the temperature 0 Kelvin and the pressure 1 trillion atmospheres? Because that way I'm going to get all products. Or will there be problems with these two? There's one thing that the equilibrium does not take into account. Well, actually, I lie. There's lots of things. Cost, safety, and rates of reaction. All this tells us, and all we're doing is increasing the amount of ammonia that we have when the reaction is complete. If we drop the temperature too low, I mean 0 Kelvin is slightly extreme, but what happens to the rate of reaction as we decrease the temperature? Come on, my grade 10s know this. What happens to the rate of reaction as we drop the temp? So the rate of reaction decreases. So if we drop the temperature too low, the rate of reaction will slow down and it will take too long to reach equilibrium. So what could we add? I don't think we've gone over this. Maybe we went over it a couple weeks ago. But what could I add to this that won't affect the equilibrium, but will bring our rate of reaction back up? Catalyst, very good. Who wants to explain what a catalyst is or what it does? Kai, very good. But how does it speed things up? What does it do? Maybe if I draw the graph, it'll jog your memory. Lowers the activation energy. So it lowers the amount of energy required for the reaction to take place. So we can drop the temperature. I mean, this reaction still happens at like 300 degrees Celsius. So, I mean, we're not dropping it down too much. But by utilizing a catalyst, we can lower the activation energy for the reaction to take place at a reasonable speed. Inorganic catalysts are normally metal oxides. So for this, you would use magnetite. This is a mixture of Fe2+ and Fe3+ bound to oxygen. If you were running this reaction, Would you place a huge chunk of magnetite in there, or would you grind it up as finely as possible? Yeah, so you grind it up as small as possible to ensure the maximum amount of surface area is exposed. Are the catalysts used up in the reaction? No, they are not. They don't actually take place. They aren't involved in this reaction at all. So they can be kind of reused over and over. If this reaction takes place at about 250 degrees Celsius, in reality, would it be appropriate to use an enzyme or a biocatalyst in this case? What would happen if we stuck an enzyme in at 250 degrees Celsius? No. The enzyme would denature. So the only thing we could use is magnetite, which is an inorganic catalyst. All right. So that's the Haber process and all of the equilibrium stuff. There's one more that's called the contact process. The contact process is what we use to make sulfuric acid. There's 3 steps. The first step is not reversible. The second step is, and hopefully you see the similarities, even though they're completely different. So we've got, these are all gases, by the way. We've got a little equilibrium sign. So if you ever see these kinds of question in your exam, is it exothermic, is it endothermic? And which side has the most number of gas? So which side, the products or reactants, has the highest number of gas molecules? Reactants, very good. Okay, so this will test if you were listening. What would happen if I increase the pressure? And try not to answer it in the chat for like 30 seconds or so. Just give everyone that. My voice is getting better. Yay.
what was that in?
Right. So what happens if I increase the pressure? Yeah, but what happens to the reaction? Which way is it going to go? Okay. So exactly the same. The reaction is going to go forwards to reduce the number of gas molecules and increase the products. What if I reduce the volume by 1/4? And if you know the answer, chuck it in the chat. I'm really just trying to trick you here. Yep, Kai, it increases the pressure, which would send the reaction forwards, because the system would try and decrease the number of moles of gas. So here's one that let's see what if I add more O2? Which way is the equilibrium going to send the reaction? So if I'm adding more reactants, how is the system going to balance that out? So Kai says forwards. Kai would be correct. Now, who remembers the collision theory of reactions? So in order for the SO2 and O2 to react, they have to find each other and crash into each other under the right conditions. If you add more O2, it will push towards the right until you add too much, then it actually sends the reaction the other way. So the answer to that question in an exam is by adding more O2, you will increase the fraction of the product, but if you add too much, you'll actually send it back the other way. Because when you add too much O2, there's inefficient collisions between SO2 and O2. What if I increase pressure. Oh, we just did pressure, sorry, the temperature. We'll run 20 seconds to have a think. So Noah, why does it favor the reverse reaction? Yeah, because it's going to try and suck heat away from, yeah, it wants to lose temperature. It wants to get back to equilibrium. All right, what about if I, again, you guys, what about if I drop the temperature? Yeah, it's going to go forwards. All right, the whole point of this unit is to put everything you've learned about chemistry into practice. Or why we call it industrial chemistry. Industrial chemistry, right? So we're looking at producing products we have to consider safety, cost, practicality, the next couple of sessions we're going to look at green chemistry. Very exciting topic. Going to look at mass spectrometry. And how we can use all of this to ensure safety, protect the environment, ensure it's cost effective, and that it's practical. We know that if we increase the pressure, we will get a greater return. But we also know that if we increase the pressure to 1 million atmospheres, we're going to create a very large bomb. It's not safe. So there's a limit to the pressure because of safety concerns. It's not cheap to produce a lot of pressure. It uses a lot of energy, so it's not good for the environment. It's not practical to build a pressure chamber that can withstand 1 million atmospheres of pressure just to make ammonia. Ammonia needs to be cheap sulfuric acid needs to be cheap. Sulfuric acid is the most widely used industrial chemical. So we're going to look next week at green chemistry and the principles of green chemistry and how we can use chemistry to solve a lot of problems that chemistry itself has created. So things like looking at methods of production of plastic. So we look at biofuels, we look at bioplastic, all things that came about from chemistry that we now need to use chemistry to come up with a solution for. So I will see you guys next week. I accidentally uploaded a methods recording to this one for last week, so I need to redo that now. And I will see you guys next week.